oil rig. Oxidation is loss of electrons or electron density. Reduction is gain of electrons or electron density. I like to think of things in terms of electron density because in biochemistry often we're dealing with like changes in where the electrons like to hang out rather than actually being able to see electrons swapping hands between different atoms. And so what the heck am I talking about? I kind of just jumped right in. So let's step back and think about these dogs and these poker chips. Don't worry, hopefully that'll make more sense in a minute.
So the periodic table, which lists all of the different elements, carbon, hydrogen, nitrogen, phosphorus, sulfur, all of these, it can seem pretty overwhelming. You have all of this diversity, all of these different elements, but really it comes down to at their heart, they're all made up of these same subatomic particles, these same even smaller parts. You have the protons, the neutrons, and the electrons. Another simplifying thing is that this is biochemistry, we're typically dealing with just a small subset of the periodic table. But if we just understand those fundamental subatomic particles, then we can kind of think in the terms of being an atom and what would you want. So in an atom, these subatomic particles, we have the protons, these are positively charged, the neutrons, these are neutral, and the electrons, which are negatively charged. Now, the protons and the neutrons that hang out in the very center of the atom in this dense central nucleus. And the neutrons kind of help glue all those protons together. They need that glue because they're all positively charged. Like charges repel each other. And so if they didn't have some sort of like help getting held together, then they'd be repelling one another. The positive charge has task of helping rein in those negatively charged electrons. So the negatively charged electrons, they're super duper duper tiny. I mean, all of these were tiny, but these are like super duper tiny. And they're whizzing around in this electron cloud around that central nucleus. And the protons have the job of kind of helping rein them in. Because these electrons, so we can kind of picture them as we often picture them as being in these like shells or these orbitals. But those are really just the places where they're most likely to hang out. We can never know exactly where an electron is. And really it's more just in terms of like, we can think of this electron density, this cloud, and you can have the cloud shaped in different ways where the different orbitals say there's more electrons over here or more electrons over here at any given time. So if you were trying to like put a tracker on one of the electrons, where would you, and then mark it over time? Or one of those, like, have you ever been to like the exploratorium where they have that robot which has like the marker and it like draws out the thing? It would be like that. Like, where would you find the most of that marker? So we can think about the electrons as kind of liking to hang out in different places more or less. And this is going to be a key concept that's going to come into play when we're thinking about the concepts of electronegativity, which is representing kind of like which atom is more likely to be able to draw that electron density towards it. And then with the concept of oxidation and reduction, you think oxidation is locus of electron density and reduction in gain in electron density. So we're thinking about where these electrons are hanging out. This is going to be really, really important because in biochemistry, we're often not dealing with actual being able to see whole electrons move like you could see in some metal reactions. Instead, we're really dealing with trying to think about where the electrons are hanging out more with, and they're going to be hanging out more with the atom that is more electronegative. And so often this is going to be like an oxygen as opposed to, say, a hydrogen. So with getting back to this idea, though, of why molecules have these different properties, why are molecules molecules? So typically we think of a molecule as being a combination of atoms that are covalently bound together. So a covalent bond is when atoms hook up. They join together pairs of electrons to form these strong covalent bonds. They kind of like merge their electron clouds. This is going to be in contrast to the idea of an ionic bond. We call them a bond, but really they're just strong attractions, where you have a fully negatively charged particle and the fully positively charged thing. So you have an anion, the negatively charged thing, and a cation, the positively charged thing. Because opposite charges attract one another, they like to hang out together. And so they like to hang out together a lot because these have full opposite charges. And so we call this like a bond, but these are not actual bonds. They're more just like a strong attraction. We can also have weaker attractions that are due to partial charges. But if the full full ionic bond, when you have an actual ion, you have this full formal charge. Formal charge, you have an actual imbalance of protons and electrons. So protons and electrons, they are equal and oppositely charged. So if you have a neutral molecule, you have an equal number of protons and electrons. If you have a charged molecule, then you have an imbalance. And so why would you have a charged molecule? Well, because those electrons are really energetic, because those electrons are like held out all the way out here. Remember, the protons are trying to rein them in. Those electrons, they like to move around and they can kind of get wooed by other molecules. So they can leave, and they can leave and go to a more electronegative atom, an atom that is better at wooing it. And so this is what we see if we look at something like sodium chloride. The chlorine is better at wooing the electron, and it can actually take that electron, that extra electron from the sodium. And then they both win because this leaves them both with an octet. So this brings us back to another important concept, is that these atoms like to have this like a full outer shell. So remember that they're not actually like shells like an onion, but there are these different orbitals and things that we can think of in an electron or in an atom where the electrons like to hang out with most. And it turns out that these atoms like to hang out. The atoms are most stable when they have a full outer shell. For the atoms that we're often dealing with in biochemistry, we're talking about these like main group atoms. We're here that typically like to have an octet. So this means their full outer shell is 8 electrons. And for hydrogen, your full outer shell will be 2 electrons. This gives them the electronic configuration of one of these the ones in this 8th column. This is like the noble gases, and these are why noble gases are really inert or non-reactive, because they have a full outer shell, and everyone else wants to be like them, so they're going to try to get that full outer shell, but they're kind of like in their neutral form. They would have the equal number of protons and electrons. The number of protons is what defines the atom. It's what defines the element. So say hydrogen, you have a number 1 here, that means it has 1 proton. So in its neutral form, it would also have 1 electron. What about oxygen? 8. Okay, so this means that it has 8 protons, and so in its neutral form, it also has 8 electrons. Because of this whole like shell thing, it has 2 in the inner shell and then 6 in the outer shell. We call the ones in the outer shell the valence electrons, and they're more reactive. And so these are the ones that can be given and taken in order to form bonds, or in order given or taken or shared, which is what happens. You can share electrons to form bonds, and this kind of is a win-win situation for different atoms, that they can share pairs of electrons to form bonds. Okay, so when they share pairs of electrons to form bonds, they can share a single pair for a single bond or 2 pairs for a double bond. And then again, this is like, so if you think of like oxygen hanging out, well, now they can help. If an oxygen, remember it had 6, it wants 8 in that outer shell, and so it can share one each with, it can share with a hydrogen with another oxygen, and this is going to give it that full outer shell. And so win-win, right? But it's not an even share when it's sharing with this hydrogen. This gets to the concept of electronegativity, and this is why we're going to see how we can have oxidation and reduction reactions occur even if we're not seeing actual like full electrons changing hands. So electronegativity is basically how hoggy an atom is on the electrons that it's sharing or the electrons that it holds. And so when I think about electronegativity, I like to think in terms of dog walkers. So if we think of the nucleus, so if we think of where the protons are and everything, we can think of this as our dog walker. And our dog walker is going to be basically each element is going to have a certain set dog walker in terms of the characteristics. Like this isn't going to change. You can't change the number of protons. You can't, or you'd be a different element. So your dog walker is kind of like defined. But the number of dogs that dog walker can have can vary. So the number of electrons can vary, even though the number of protons stays constant. Different dog walkers are going to have a better pull over their dogs. So the leashes can be different strengths. And the stronger that leash is, the more electronegative the atom is. And therefore, the more likely that the electrons are to hang out around that atom. So if you have atoms sharing pairs of electrons, the electrons are going to want to kind of hang out more with the more electronegative atom. So what happens if you have atoms that are shared in a covalent bond? So you have these atoms that are sharing pairs, you have electrons that are shared in a covalent bonds between different atoms. The electrons, when you have those like merged electron clouds, the electrons, it's not like they know like, oh yeah, I belong with that oxygen, or oh yeah, I belong with that hydrogen. Really now, because you have these kind of like merged clouds, these electrons are free to roam kind of between them. They're going to hang out more with the one that is more electronegative, so the one that's better at moving them. This is going to mean that you have more of the electron density by that better wooer, by that more electronegative atom. We can look at trends on the periodic table to see where the more electronegative ones are going to be, and we find them in this upper right corner. This is for various reasons, including that their electron that the outer electrons, so those are the ones that can move around more and are more reactive, those outer electrons are going to be closer to the nucleus. So when you get further away, it's going to be harder for the protons in the nucleus to rein in those electrons. So you can think of it kind of like the dog walkers calling to the dogs, but the dogs can't hear you because they're too far away. And then you can think about so that's like on the up and down, because as you get further down the table, you're getting farther and farther away from the nucleus. You're adding more and more shells in between the nucleus and those outer electrons. So what about if we look in the upper, why is it like the right? So as you go to the right, you can think of you're gaining more protons. So our dog walkers are getting stronger. Your leashes are getting stronger. So as we go up the periodic table, we're getting closer. So we're getting like louder. And then as we go to the right, we're getting stronger. And so when you look in the upper right corner, you find these really electronegative atoms. And the one that we deal with a lot and the ones we deal with a lot in biochemistry are going to be nitrogen and especially oxygen. And so when we think about redox reactions like reduction and oxidation, so oxidation is like, you think it would always involve oxygen, but it doesn't always involve oxygen. But it often involves oxygen because oxygen is so electronegative. And so if something gets bound to oxygen, it is oxidized. It becomes because it's going to be losing electron density to that oxygen, because that oxygen is going to hog the electrons that they have in that shared pair. And so it's like that electron, or like that atom is losing electrons when it's losing this electron density. And so if you were to take that marker that was drawing out where the position of all the electrons, now the positions are going to be hanging out more around that oxygen. So those electrons might have originally belonged to the first dog. Now they're going to be hanging out more with the second dog. So we can think of these bonds in different ways. So remember that these atoms are trying to form these like full outer shells, and there's different ways that they can go about that. And this depends on, say, how electronegative the atom is, how close to that full shell are they, various things like that. When you have the elements, sometimes what they can do is, especially if you have like one on this far left side and then one close to the far right side, you can get these actual like ionic bonds. And so remember, these aren't actual bonds; these are just These are just atoms with formal charges, so they have an actual imbalance of protons and electrons. And because they have these full opposite charge attractions or opposite charges, they're going to be attracted to one another. And we see this if we look at the formal charge. And so these are real charges, not just hypothetical ones. We're going to be talking a lot about hypothetical charges when we talk about oxidation numbers. But in the case of these ionic ions, we have actual formal charges. And so we take the number to find the formal charge of an atom. We take the number of protons that it has, and remember this defines the element. And this is also going to tell us what number of electrons the atom has in its neutral form. So remember, protons and electrons are opposite equal and but oppositely charged. And so in order to have a neutral molecule, you'd have to have an equal number of electrons to the number of protons. And the number of protons is what defines the element. And that's what you're going to see when they look at the periodic table and see what that number is that's above the element name. And so, for example, chlorine, we look over here, we see it has 17. And so this means that in its outer shell, it's going to have 7 electrons in that outer shell because it has 2 in that inner shell, and then it has 8, so that would be 10, and then it has 7 in the next shell. So in its outer shell is going to have 7 electrons. So 17 overall, but 7 in this valence, 7 valence electrons. And so it's really close to that octet, but not quite there. What if we look at sodium? Well, here we have 11. So we have 2 in this inner shell, 2 in this shell. So that's 10. And then we have 1 left over, so we have 1 valence electron. And so in its neutral form, it's going to have 1 valence electron. And now what's going to happen is that when you get those ionic forms, so you have 1 extra, you have 1 missing, and this chlorine is really good at getting the upper right corner. It's really good at convincing this dog to leave this dog walker all by itself. So it's kind of, you can think of a dog as like oh, if it sees a squirrel, it's going to run and try to chase that squirrel, and it's going to leave this dog walker, leave the sodium, and join the chlorine. Because you're actually losing this full electron, now you're going to end up with a charge of -1. So you take the number of electrons that it had, so the valence electrons it had was 7. It now has 8. So 7 minus 8 is -1. So you have a formal charge of -1. What about sodium? It had a valence electron. It lost that valence electron. So now it has 0. So 1 minus 0 is +1. So it has a formal charge of +1. Okay, so those are formal charges. But what about in a shared bond? So we would think that in a shared bond, you have the neutral molecule, right? So there's no formal charge, but you can still have oxidation numbers, and you can still have like what are like hypothetical charges. So basically, if those atoms were to split up, so they're not split up, they're hanging out together. Those electron clouds are merged, so they're actual covalently bonds. It's not like it's not like one of the atoms owns the electron and the other one doesn't. They're sharing them. But say you were to split them up, which way would they split? Which way would they be happiest with? So I always think of like the movie Annie, where they're like, come here, which like they're both calling the dog, and like who would the dog go to? And so that's the kind of, we can think of it like this: like if these dog walkers were to get divorced, who would the dogs want to go with? And they are going to want to go with the more electronegative atom. So if we can calculate this kind of like hypothetical charge that we would get if they were to split up, if they were to be an ionic bond rather than a covalent bond. So if they were to just be like hanging out together but not actually merged, what would their formal charges be? If we think about hydrogen, the neutral form has one electron. If you were to split up this hydrogen as H2 molecule, they were sharing fairly, they would each get one electron and you'd have an oxidation number of 0. So when you have atoms that are the same elements, they're both equally good at holding on to the electron. So if they were to split, one would go with either, and then you wouldn't have a change in the oxidation state. Whenever you have a pure element, so it's just the element by itself, its oxidation number is going to be 0. Okay, well, what if you have molecules bound together that are unequal sharers? There can be a variation in how unequal the sharing is, and we'll get to this in a minute. But the atoms are going to want to go to those like dogs, those electrons are going to want to go to the more electronegative atom, the nicer dog walker, the louder dog walker, the stronger dog walker. And if you're dealing, say, with water where you have an oxygen and 2 hydrogens, well, hydrogen's really bad at holding on to that electron because, well, the hydrogen, it only has a single proton. It's not very good at holding on to that electron. And the oxygen, it has all those protons. It's got really great pulling power. So it's going to be very hoggy of the electrons and is able to woo those hydrogens electrons. And so even if the hydrogen protons leave, the electrons stay. And this is what we're going to see when we talk about deprotonation. And so we have the electrons here are going to be wanting to go with the oxygen. If we take the neutral form of oxygen, it has 6 valence electrons. So it has 2 in the outer shell, 2 in the inner shell, 6 in the outer shell. And if you were to split them up like this, well, then how many electrons would it have? It would have 8. 6 minus 8 is -2, so it has an oxidation number of -2. What about the hydrogen? So the neutral form of hydrogen has 1 electron, and it only has, so the only single shell, so it's in the valence shell, it has 1 valence electron. If in this case, it would end up with 0, so it would have an oxidation number of +1. So even though we're not actually splitting these up, we can still assign them these like hypothetical charges. And in this case, we call these hypothetical charges their oxidation number. When it comes to just try to figure out like which atom was more electronegative, which atom would be able to own the electrons in the split up. If those dog walkers split up, who would the electrons want to hang out with more? I like the dog analogy for that. When it comes to actually thinking about the formal electron, formal oxidation number things, I like to think in terms of poker chips. So you can think of, you can look to the group numbers, so it's like 1, 2, 3, 4, 5, 6, 7, 8. These are the group numbers. And you can look to that to see how many valence electrons an element has in its neutral form. This is going to, because we need to know this in order to know like what would it end up with, compare. So if you're in this column 1, so hydrogen and sodium have 1. If you're over here, carbon has 4, oxygen has 6. It's group 6, and chlorine has 7, and it's group 7. And so we can think about this. So I'm just showing as white, we have this valence number in the neutral form. And then in this purple and white stripe, this was like how many would own if the bond were ionic. If we subtract this number that it would own from the number that it would have in its neutral form, then we get the oxidation number. And so this is the hypothetical charge that it would have if these atoms were to actually split up. So in the example of, in this example of formic acid, we can look at each of these individually. If we think about a bond of a carbon to a hydrogen, if these were to split, who would keep? The carbon would get to keep because the hydrogen is a poor, is less electronegative and is not very good at holding on to that electron. So we said that carbon, remember we said that carbon, it started with 4, and if it ends up with 2 from this reaction, it's going to have a +2. If we think about this hydrogen, we'll get back to this carbon, but let's think about this hydrogen. This hydrogen, it has 1, and it ends up with 0 because it would have to give it to the carbon. It's a 1 minus 0. You end up with a +1 oxidation number for that hydrogen. Okay, what about this hydrogen? Well, this is the same situation, except here the hydrogen will lose out to the oxygen. And so it would have a 1 minus 0 is a +1. Okay, so now what about this oxygen? We'll take the easy ones first, the ones that are just bound to one other thing. So oxygen, we said starts with 6. And if in this situation, if it was bound to this carbon, it would get to keep the electrons that it was bound to that carbon with. And in this case, it was sharing 2 pairs of electrons. So it's going to get to keep that both 2 electrons, and so you end up with 8. If you were to have that hypothetical split, 6 minus 8 is going to be a -2. You have an oxidation number of -2. Okay, let's now look at these trickier ones which had bonded to multiple things. So this oxygen, remember, it's going to get to keep this one that was shared with the hydrogen, and it's also going to keep this one that was shared with the carbon. So it's going to end up with 8 overall. 6 minus 8 is -2. You have an oxidation number of -2. Okay, and this carbon, it's going to get to keep this one from hydrogen, but it's going to get this one stolen from the oxygen. So it's going to end up with 4 minus 2 is +2. So it has that 2 that it was shared with the hydrogen, but then it's losing the ones that it's sharing with the oxygen. So you end up with the oxidation number of +2. The sum of the oxidation numbers should equal the formal charges. And because this molecule has an overall charge of 0, we should have this equal 0 when we work this out. So if we take the oxidation numbers and we add them up, we have a -2, a +1, a +1, a +2, and a -2. So -2, +1, +1, +1, 0, +2, 2, -2, 0. So yeah, it worked. Okay, so often in metabolism, we're dealing with oxidation and reduction reactions. And so a good, as carbon gets oxidized, basically, you can think of a molecule that's good fuel as coming with a lot of poker chips. And then as you oxidize that, so often the catabolism, the breaking down of molecules, often involves oxidizing those molecules. And so a good fuel would have not that many double bonds, say, and it would have fewer bonds to oxygen. Whereas in the case of your final spent fuel, you're going to have more of the bonds to oxygen, fewer of the bonds to hydrogen. You're going to have your molecule is going to be more oxidized. And so if we think about methane, so think about methane, for example, for why this would be a good fuel, is you have if it's sharing just bonds to hydrogen, it could still own those bonds that it had to hydrogen. And so the more bonds you have to hydrogen, the more of those like freebie electrons you get. And therefore, the more opportunities there are for you to then give away those electrons. When you give away those electrons, we're talking about an oxidation reaction. And in those cases, we can take those electrons, we can actually channel them through various metabolic pathways. We can put them onto like NAD and stuff, and then shuttle them to the electron transport chain in the mitochondria and use them to make ATP. And so we can take advantage of these electrons, but you need to have those electrons to start with. And so if you have a molecule that is in this reduced state that has a lot of bonds to hydrogen, say, it's got a lot of electrons that it can be used for fuel. If you form bonds to oxygen, well, here this is not as good of a fuel because now the oxygen will get to keep those electrons. And so, in terms of thinking about the carbon, well, now it has an oxidation number of -2. And you can see that as a molecule gets oxidized, you increase the oxidation number. As a molecule gets reduced, you reduce the oxidation number. And these can go back and forth. And so, molecules can, it's not like it's a one-way street. You can have oxidation and reduction going different pathways. Often in our bodies, these are catalyzed by different enzymes, so different reaction helpers, different proteins. Oftentimes, however, they're done by the same protein because enzymes can only facilitate the reaction. They can't make it happen. They can't make a reaction happen that doesn't want to happen. It's like a horse, leading a horse to water, you can't make them drink. Enzymes can put molecules in the right orientation and things and get them close together so that they're more likely to react, but they can't actually make them react. And so if the reaction is really unfavorable, you often have a different enzyme to do it the other direction, but the reaction is more easily reversible, and it's often the same enzyme in very different conditions, different concentrations, things like that. But anyway, more on that in other posts. So as you form more bonds to oxygen, the carbon is going to be getting oxidized, and you can see that its oxidation number is increasing. Currently, we've been talking in terms of the carbon. If we were to think about where the carbon is getting the oxygen from, a redox reaction, you always have to have oxidation and reduction. So we call it redox, or reduction oxidation. You can't have one without the other. And often we're thinking about in terms of one of them, but really you have to remember that there's the other reaction happening as well. And so if something's getting oxidized, something else has to be getting reduced, and vice versa. So if we think about where the oxygen is coming from, if that oxygen is coming from molecular oxygen, which molecular oxygen has an oxidation number of 0. So if you had from molecular oxygen to this state where the oxygen has a -2, well, here you would, that oxygen would have been reduced. So the oxygen, molecular oxygen, would be reduced as the carbon gets oxidized. And so you always have to be thinking in terms of redox and reactions. So one thing happening in the other. The thing that gains the electron density, or the electrons, so the shared electrons, it's getting reduced, and it had to oxidize something else to do it. So it's called an oxidant or an oxidizing agent. The thing that loses electron density, so the thing that gets oxidized, had to reduce something else to do it, so it's called a reductant or reducing agent. So in the case of this, these reactions, if we're increasing the oxidation number of carbon, carbon is getting oxidized, so carbon is acting as a reducing agent or a reductant. Wherever that oxygen is coming from, it would be acting as an oxidant, and so it would be acting as an oxidant, and it would be getting reduced. I often I struggle with these terms a lot. Kind of mixing it up in my head because you have the oxidation is losing electrons. So the oxidant is going to be the one that causes the other to lose. So it's going to be gaining. And so it's confusing when you think about that. So I really have to think through when I'm talking about it. So hopefully I haven't messed it up a lot. Okay, so let's think about an OH. So think about this OH being attached to some other molecule. So there's some other bond here. If you were to hypothetically split them, split the hydrogen from the oxygen, just like before, the electron that originally came from that hydrogen is going to want to stay with that oxygen because the oxygen is more electronegative. What happens when this often actually does happen, this is deprotonation. So the proton is leaving, but the electron is staying. In both of these cases, because we actually have this happening now, and so we have the ionic bond forming, and we can think, okay, well now we have this formal charge of, well, we have a formal charge of +1 and -1, but that formal charge is the same as the hypothetical charge that we had before, so we're not actually changing the oxidation numbers of oxygen or hydrogen. So when we have deprotonation, this is not a redox reaction. But if you can have reactions where the oxidation number does change, you can have these reactions where you have these redox reactions, the oxidation numbers will change when this reaction occurs. And we can see this happen in reactions involving hydrogen, just not the ones that are involving the deprotonation. We actually have to have in oxidation, it's the dog, so it's the actual electron and not just the walker, not just the proton that leaves, or the walker is getting swapped with um, with the dog that's harder to woo. And so if you have this like hypothetical ownership changing, so the oxidation state's changing. So for example, our if we take that OH and we actually remove the hydrogen with the electron, we form this like radical because these have these one unpaired electrons. But this would actually, if this is happening in a reaction or something, you would often have this just being swapped for something else. But here you have an actual loss of a hydrogen, you have that loss of the electron oxidation. The oxygen is actually losing electrons, and the hydrogen is gaining electrons, or at least gaining like what they would have been hypothetically before, because the oxygen was kind of hogging hydrogen's electrons. And if you were to split them hypothetically, they would want to split in the way the electrons shared with the oxygen. But when we're actually doing this split in this way, the electron is going with the hydrogen, and so that hydrogen gets to own that electron, which it had already started with, but then the oxygen kind of like stole it or hogged it. And so the hydrogen in this case um, is getting reduced, and the oxygen is getting oxidized. It's losing electron density, it's gaining electron density. If that oxygen was then to hook up with another oxygen, well, now it's going to have to share fairly. When we think about oxygen, like molecular oxygen, it's kind of confusing because it's like not just a single bond holding them together. But you can think about these two oxygens, they're having to share fairly. And because they're sharing fairly, they're going to have basically the oxidation number isn't going to be any different than if you just had that single oxygen. So you're going to have an oxidation number of 0 whenever you have any sort of element in its molecular form, where it's like just hanging out by itself. So it's important to remember that when we have these deprotonation reactions, these are not redox reactions, because a proton doesn't have any electrons to give. By definition, a proton is just a proton, and so it's this H plus because the hydrogen has one proton to begin with. In its neutral form, it has a proton and an electron. Normal water doesn't have like any neutrons, it just has a proton and an electron. And so when we have, you lose that electron, now you just have a proton. This is why we call H plus a proton. But if you gain or lose an actual neutral hydrogen atom, then that is a redox reaction because you're dealing with oxidation, with changes in the number of electrons. Because hydrogen has that weak pull over the electrons, it's kind of easily pulled away. That electron is kind of easily pulled away, and it's not very electronegative. And so therefore, if something forms a bond to a hydrogen, it's basically like a free electron in terms of our hypothetical charges, in terms of our oxidation state. That thing is likely going to be able to hog that electron density. Therefore, because remember, oxidation is loss of electron density, Reduction is gain of electron density. Often when something is bound to forms a bond to hydrogen, it's going to be gaining electron density because it kind of gets that freebie electron from that hydrogen. Whereas if something loses a hydrogen atom, then it's going to be losing electron density because it was kind of like it's losing that free electron that it had. And so we can think about if we go, say, from a methanol to formaldehyde, we're forming another bond to the oxygen, or we're losing a bond to the hydrogen. We're having a redox reaction happening here. And we can see this when we talk about the formal charges that these atoms would have if they broke up. And so in this case, we would have remember the formal charges is the number of in their valence electrons in the neutral form minus the number that they would have if they were to be in ionic bonds. So if those bonds were to actually split, who would the electrons most like to hang out with? When this carbon is hanging out with the hydrogens, the hydrogen is going to get to kind of like own those electrons from the hydrogen. And the oxygen is going to get to own the electron it held with the hydrogen. Well, now what happens is if you take away that hydrogen, well, then the oxygen then the oxygen forms a bond to this carbon. The carbon is losing this bond to the hydrogen, and it's forming a bond to the oxygen. So it took one that was it got to like keep, and now it's getting swapped it for one where it's getting taken away. And so you end up with this you end up with like a +2 overall effect, giving you an oxidation state of 0 for this carbon. If we think about going a step further and going to formaldehyde, well, here in our carbon, this carbon state, we're going to have this carbon. What's happened here is it's formed another bond to oxygen. It's given up a bond to hydrogen. And so you're going to get another +2 bump because you lost one that you had, and then you lost another one because you're forming a bond to oxygen, which is going to take one of the ones that you had been owning. And so now you're going to get that +2 overall. But the key is that in all of these cases, you're actually gaining or losing electrons. And you can see that when you form a bond to oxygen, that's typically an oxidation reaction. You're losing electron density because the oxygen is a better hog. Similarly, when you gain a bond to hydrogen, it's like you're getting free electrons. So that would be a reduction, a gain in electrons. And remember, we're talking about like electron density because they're not actually like, it's not that these like individual electrons are getting swapped or whatever. In these cases, the electrons will share. But in this hypothetical situation, this hypothetical charge, it would be hanging out more with the atom the hydrogen is bound to. And then if you swap the hydrogen for an oxygen, well, now the oxygen is going to be owning the electrons in that situation. So this is why we see that reduction is often, but not always, associated with a gain to hydrogen or a loss to oxygen, and then reduction. Oxidation is often, but not always, accompanied by a gain of a bond to oxygen, or a loss of a bond to hydrogen. But if you have a deprotonation reaction, so if you go, say, from formic acid to formate, here you're just losing that proton. And because that oxygen would have owned it already, there's no electron lost in this interaction. There's no change in the redox numbers of either of these compounds. And this is not a redox reaction. But another confusing thing about chemistry is we're often dealing, remember, with this electron density rather than actual electrons, actual like individual electrons. And so it's easier to think about in terms of the ownership of those electrons. Where would the electrons hang out with more? They're going to hang out more with the one that's more electronegative. So if something is forms a bond to something that gets those electrons, that thing is more electronegative. Those electrons that they were sharing get pulled away more. Then that thing has been oxidized, even if you can't see that there's an actual electron being lost. And often, but not always, this is associated with the bond to oxygen. Because oxygen is really electronegative, it's going to be hogging those shared electrons. If we think about those electrons form a bond, the electrons are pulled closer. Well, now that atom has been reduced, it has more of that electron density. This often, but not always, occurs with the bond to hydrogen, because hydrogen is it's less electronegative. So it's kind of like a freebie electron if you form a bond to it.